So hello again. Short video about other examples of calculation in Z over NZ with, I think this time, some results that will look quite strange or quite different from what you know about standard calculation with numbers. So let's start with the first example. So in Z over 18Z, compute 9 bar plus 10 bar. This one is quite easy. It's equal to 19 bar, which is equal to 1 bar, because we do here calculation modulo 18 as n is equal to 18. 5 bar plus 13 bar, so 5 plus 13 is 18, and actually with simplification modulo 18 it's 0 bar. So that's can happen. That happens actually. You have a sum of two elements where the results is equal to 0 bar. So actually, this means that when you have two elements, two numbers, which sum is equal to 0 or 0 bar, it's a way that these elements are defined as opposites. Actually, we can define opposites without using the minus sign. So 5 bar is the opposite of 13 bar. And actually the reciprocal is also true. 13 bar is also the opposite of 5 bars. So opposites always go by 2. So next about multiplication. So we always apply the same rules that we've seen before. Actually, 7 bar times 6 bar is 7 times 6, which is 42 bar. And if we make a simplification modulo 18, actually let's write it just as a reminder. 42 divided by 18, the quotient is 2. 2 times 18 is 36, so the remainder is 6. So actually 42 modulo 18 is equal to 6, and the result is 6 bar. So that things can happen that when you multiply two elements one by another, you can find one of the two, and that's not an error. Maybe it's a bit strange or shocking for you, but that can happen in Z over NZ. So next example, 9 bar times 4 bar. So 9 times 4 is 36. 36 bar, actually, modulo 18 is equal to 0. So here is another strange thing that doesn't happen in a standard set of numbers you know, such as a set of natural, rational, real, or complex number. Here, something can happen where the product of two elements which are different from 0 give a result which is equal to 0. So actually 9 bar and 4 bar are called divisors of 0 bar. And that's not an error. It's due to the structure of Z over NZ itself, and some values. I will talk you later how to know which element are divisors of 0 and which element are not. So last example, 7 bar times 13 bar. 7 times 13 is 91 bar. So once again, if we do the Euclidean division of 91 by 80, the quotient is 5. 5 times 18 is equal to 90. So the remainder is 1. So 7 bar times 13 bar is equal to 1 bar. We can see here that actually we can take two different values from the Z over NZ set, and their product is equal to 1 bar. So actually, this defines the relation of having inverses. Actually, when you multiply two numbers and the result is 1, then those numbers are inverses. The same thing is true in Z over NZ, even if the numbers are not written in a standard way. Here, 7 bar and 13 bar are inverses, one of each other, and this is true in Z over 18Z. Remember that when the value of n changes, the result of the operation also change, so that you can't state that 7 bar and 30 bar are inverses whatever the value of n. They are inverses with respect to the value of n. So that's true in Z over 18Z. That might be false for in Z over 19Z or Z over 20Z or whatever value of n. So please remember that all the results of the calculation done as an example in this video are always done for n equal to 18. And that's how simplification is made possible, so that all the final results here have a value between 0 and 17.